Okay guys, Mr. Martin back with a video on symmetry and dilations. This covers section 9.5 and 9.6, and it will also conclude section chapter 9 and section 6.1. So in this section, I'll let you guys see what we should be able to do once we finish this lesson. All right, so get your notes, piece of graph paper, and possibly a calculator. All right, so first we're going to talk about lines of symmetry. A line of symmetry is a line that you can draw through a figure that would reflect the figure onto itself. I'm going to jump over to paint for a moment so we can see this. So now that we're in paint, all right, so I'm going to grab a line and we'll make this line red. So for this triangle, we can draw a line like right here. I'm going to try to move that a little bit. Well, this is good enough. I will move it over just a little bit. So now we can see that for this line, if we flip this figure from here to right here, highlight these 2 points. Where's my brush? So if we flip this figure from this point over to this point, that coordinate would map onto itself, and everything on this line would line up with everything on this line. So this figure has one line of symmetry. For this second figure, now we can just kind of tell by looking that it has no lines of symmetry. The two easiest lines of symmetry to check are either a horizontal line of symmetry, and that didn't work, so we will say that's no. And then we can try a vertical line of symmetry, and that also does not happen. We can check diagonally, it doesn't happen, and we can check diagonally in this direction, it does not happen. So the second figure, this quadrilateral, has 0 lines of symmetry. Lastly, if we look at this rectangle, it's not perfect, but we can pretty much see that we can divide this rectangle in half horizontally, so we get one line of symmetry. Then if we come back with a different color, something that's not red, like purple later on. So now then, if we take this, we get another line of symmetry, and we'll color this one purple. So we get 2 lines of symmetry here. Now the important thing is to not confuse symmetry, lines of symmetry, with lines that divide the figure in half. So I'm going to draw on another line that goes from this bottom left corner to the top right corner. We'll color this green. Now notice this green line does divide this segment into equal parts, but if we folded this figure from here over the line, this point would end up somewhere down here, and it wouldn't actually hit right here where we would need it to have a point of symmetry. So lines of symmetry always divide a segment into equal parts by folding on the line of symmetry. All of the points must line up with each other. So that's lines of symmetry. Next, I want you guys to determine the number of lines of symmetry for each of these figures. I encourage you to pause the video and join me once you think you have the answers. Okay, so we see that the first figure has 4 lines of symmetry, and the last 2 each have 1 line of symmetry, and both of those are through the horizontal line. So next we're going to move on to rotational symmetry. Rotational symmetry occurs by rotating a figure a specific angle that is found between 0 and 360 degrees. If each time that you achieve symmetry by rotation, we call that 1 order of symmetry. So we're going to start with this figure here, and we're going to rotate it until we get back to where we start and see how many. We'll see what the order of symmetry is. So we rotate, we get 1 order of symmetry, 2, 3, 4, 5, 6, 7, and 8 is back where we started. So we get an order of 8. Now, if we want to determine the angle that we're rotating each time to achieve symmetry, we have this formula down here where we divide 360 by the order. So in this case, it's going to be 360 divided by 8, and we know that that is 45 degrees. So each time we rotate this figure 45 degrees, we achieve one order of symmetry. So I want you guys to, on this slide, determine the order and magnitude for each figure. So if you want to, you can get this PowerPoint on my Fusion page, and you can follow along that way and see what I'm doing, like split screen it. Anyway, pause the video, see if you can determine the order and magnitude or angle of symmetry for each of these figures. And when you're ready, hit play again, and I'll be here. Okay, so for this first figure, we can see by rotating, if we rotate like 90 degrees, we get nothing. 180, we get nothing. 270, we get nothing. It's not until we hit 360 degrees that that figure lines back up. So this first figure has an order of 1, and therefore a magnitude or angle of symmetry of 360 degrees. The second figure, if we rotate 90 degrees, we end up right here. We rotate 180, we end up right here. So that's 1. We rotate 270, we get nothing. And when we end up back at 360, we get 2. So in this case, the order of symmetry for this double arrow is 2, and the angle of symmetry is 360 divided by 2, which is 180 degrees. Lastly, for this lightning bolt, we can quickly see that if we rotate this around, we only get symmetry if we end up back where we started. So from this, we should see that every figure has an order of symmetry of at least 1, because you can always rotate 360 degrees to end up back at the start point. So next we have plane symmetry. Plane symmetry is when you take a 3-dimensional figure, and similar to line symmetry where you can reflect a 2D figure over a line, in this case we can reflect a 3-dimensional figure over a plane. So this plane S that is shown is not the only plane of symmetry. We have a plane of symmetry that we could draw from B, this unnamed point, in S that would go vertically down the middle of this rectangular prism. We also have a plane that we could draw from DC to F that would make another, not from DC to F, I'm sorry, from what would be in the center of this box, making a diagonal going down from this unnamed point. The unnamed points would make another plane of symmetry. If we move to the next slide, we can see more examples. So we have ACG as a plane of symmetry. And in the second picture, we have 3 different planes of symmetry. So once we add in 3 dimensions, we add on many more many more types of symmetry, plane symmetry, because there are more options, because there are more sides to choose from. Next, after we have plane symmetry for a 3-dimensional figure, we have what we call axis symmetry, which is similar to rotational symmetry, and there's a video that goes along with this. We won't watch the whole video, but I do want you guys to get the idea of what happens when we have axis symmetry. So this video loaded pretty quickly. So, all right, we'll jump in.
This is a demonstration on rotational symmetry for a cube. Now.
So we'll play the first minute of this, and then we'll just move ahead. You can watch the whole video on, if you would like, but it's found in the PowerPoint. But I'm going to move ahead after about a minute.
Consider this cube. When we rotate the cube about this axis for 360 degrees, we can see that the cube matches itself for 1, 2, 3, 4 times. With this, we can say that this axis is the axis of rotational symmetry of order 4. Now, this cube has more than one axis of rotational symmetry. Let's explore them one by one. This is the second axis of rotational symmetry. When we rotate the cube about this axis, we can see that the cube matches itself 1, 2, 3, 4 times. Hence, this axis of symmetry has order of 4. As for the third axis of rotational symmetry, it has order of 1, 2, 3, 4. For the fourth axis, this axis has the order of 1, 2, 3. For the fifth axis, this axis has the order of.
Okay, so we can see that similar to rotational symmetry, every three-dimensional figure has at least an axis of symmetry that could go through the center of the figure, and we could rotate it at least to 360 degrees to achieve one order of rotational symmetry. So again, I do encourage you guys to download this PowerPoint found on my Fusion page, and you can follow along in the PowerPoint and manipulate this stuff as I've been doing in the video. So now that's going to conclude section